in that case, recording now. It's our seventh lecture. It's about compactness, a concept we have not seen, even in on the real line. We didn't see it last semester. And for this, Tao does a little bit of a weird thing as well. Tao gives the definition of what we're going to call sequential compactness as the definition of compactness. Now we're going to prove a theorem that says sequential compactness and compactness are the same thing. But until then, I want to give what I consider to be the standard definition of compactness. And then we'll prove it's the same thing as Tao's definition. Now, so what this means is that for the whole time we're going to talk about compactness, which our syllabus says is 2 lectures, but I think is going to be 3 lectures. I'm going to be supplying lecture notes. Okay? So Tao's coverage of compactness will hopefully make sense after we're done with all 3 of these lectures, but it might not make sense now. Or, I mean, it'll make sense, but it might not kind of make sense with what we're doing in class. Okay? So here's the definition of compactness. Okay, and it's a little bit long-winded. So, and in fact, we're going to do a couple definitions right here. So we start with a metric space and a set. First, we're going to define what an open cover of that set is. And again, that's something we haven't talked about yet. Okay. An open cover is a family U, and I'm going to use a script U for the family of open sets such that S is contained in their union. So the union would be the union of all the sets U that are in the family script U. Okay, so we haven't gotten to compactness yet, but we'll let's stop for a second and see what an open cover is. Remember, a family of sets is just a set of sets, but usually we use family, so we don't have to say set of sets. And then the cover part, well, the open part is just that they have to be open sets. And then the cover part is this. They cover S in the sense that every point in S is in one of the sets in U. Okay? Any questions so far? Okay, now the second part of the definition is compactness. So a set K, and I guess I should say that's a subset of X, and it is compact if for every open cover of it there's a finite subset of that open cover, by which I mean a finite number of sets in script U that still cover it. Okay, so then there is a finite subfamily script V contained in script U such that K is contained in the union of the sets in script V.
I have a question about the term family. So does that always imply that it's infinite?
No, it doesn't have to be infinite. So the script U doesn't have to be infinite.
Okay.
I mean, if it's finite, then you've automatically got a finite subcover. Oh, right. That's the term I want to define right now. In this case, that script V is called a finite subcover. Okay. Now, this definition might kind of feel like it comes out of left field a little bit. It's going to come up again and again and again in this course because it's such a powerful idea. Like I said, we're going to spend at least 2, maybe 3 lectures on it right now.
Daddy, put your back on.
No thanks. Okay, so we should start with an example. Unless there are any more questions about the definition. Okay. In that case, our example. Well, let me foreshadow a little bit. One of our results from Monday, from the next lecture, is going to be that on the real line, the compact sets are precisely the ones that are closed and bounded. Okay, now we know other nice things about closed and bounded sets, and what we're going to see later on in the course is that all the nice things that we knew about closed and bounded sets from last semester, we can explain them all by saying that's because of compactness. Okay? And then in more general metric spaces, when we do have compactness, we're going to have similarly nice things happen. Okay, so example. Let's let K be the set 1, 1/2, 1/3, etc. The general term would be 1 over n. Except then we're also going to toss a 0 in here. And we need to say the metric space. And we're going to call our metric space RD. Just to remind you, this is going to be an ongoing convention. When we write just a metric D with the real numbers, we mean the standard metric. So the absolute value metric. This is a compact set. And let's prove that. Okay, what do we need to prove? Let's go back up and look at the definition. Now, the way to remember this definition is that any open cover has a finite subcover. Okay, this definition is a very long-winded way of saying that. Every open cover has a finite subcover. So we take an open cover and we construct a finite subcover. Okay, so let's go down here, back to our example. We are going to take an open cover. So let script U be an open cover of K. Okay, now every point in K is contained in at least one of the sets of script U, and all the sets in script U are open. So we get to use the fact that really every point in K has a neighborhood in at least one of the sets in script U. Okay? And in this example, the point to start with is 0. Okay? So, then U must contain some set U naught which itself contains 0. Okay? Now, U naught's open, so it also contains a neighborhood of 0.
Daddy, this one a book. Daddy, this one a book.
Ooh, good one. Draw on the other side now.
Yeah, no. I want that one, Daddy. I want nano pepper.
1 second. Ooh, draw on the backs of these. Those are fine. Draw on those. Okay, so there's some epsilon so that we get the epsilon neighborhood of 0 in that set. Now, the sequence 1 over n is converging to 0. So at some point that sequence is inside that neighborhood. Okay, so since 1 over n converges to 0, there is a capital N in the natural numbers such that, well, what would we get? We get 1 over n is in, oops, and I'm going to say for all n, at least capital N, the terms of the sequence 1 over n are in that epsilon ball centered at 0, which is contained in U naught. Okay, now from our perspective now, this is great. All but finitely many of our points are already in that open set that contains 0. Okay, so now we're basically done. We just have to say, well, for the finitely many that might not be in that set, since U is an open cover, it still has at least one set that contains each of them. So we'll take that one set. That's what we're going to do now. So for each n that's less than or equal to n minus 1, there is some set that contains them. Okay. And therefore, the set of sets u1, u2, up to un minus 1, together with u naught, covers K. That's our finite subcover.
So the strategy for proving compactness is going to be like shoving sequences into one of these sequences and subsequences into these open sets that are part of the cover.
Well, okay, so in general, we're not going to have sequences.
Okay.
I mean, but yeah, usually the strategy is you get all but finitely many of your points in one of the open sets, and then you argue that, well, I mean, then you're done. Then you're done.
And a second question is the reason we can't just say it's compact because we can have or we need to show for all open covers that there's a finite one. Okay, because I was thinking at first we could just do an open interval and then that's already finite, but we have to do it for all of them.
Yeah, that's a really important point. Every set in every metric space has some finite open cover. That's because the entire metric space itself is an open set. Right? So you take a set in a metric space. The metric space itself is open, so there you go. The set has an open cover with one set in it. Okay, but no, compactness means any open cover you're given will have a finite subcover. Okay. So let's go on with a non-example. So what does it look like when we're not compact? The open interval from 0 to 1, not including 0, is not compact on the real line with the standard metric. Okay. Remember, I said Monday we're going to see that subsets of the real line are compact if and only if they're closed and bounded. This one's bounded, but it's not closed. So that's what's going wrong. Okay. Now, what do we need to do to show that something is not compact?
We need to find a open cover that doesn't have a finite subcover.
Exactly. So we get to make the open cover. And some open covers might work. Some open covers might have finite subcovers. That doesn't mean anything, though. That just means try again. Okay? So we want an open cover that doesn't have a finite subcover. I'll write it down and then I'll explain why this should be what we guess. Okay? So we're going to take all these open intervals. Okay, the first one is going to go from 1 to 2. I guess we don't really care about it. The second one is going to go from 1/2 to 2. The third one is going to go from 1/4 to 2. Then 1/8 to 2. Then 1/16 to 2. Etc. Okay. We could do 1 over n there instead of 2 to the minus n. I realize the entire course we've been tending toward doing 1 over n. But actually, in this case, you know, and in most of those cases, 2 to the minus n is nicer because we don't need to worry about whether n is 0 or not. So I'm going to use 2 to the minus n here. Okay, and I claim this is an open cover. So first we need to show it is an open cover. We have, oops, 0, 1 is contained in the union of these. We agreed on that? For every real number greater than 0, there's some negative power of 2 that's smaller than it. Okay? Okay, so therefore, U is an open cover of our half-open interval. Okay, now notice here, this is a little bit different just in kind of notation than our example. In our example, we didn't have indices for our sets.
Daddy, I got my car.
Oops. Good for you. So in our example above, we just had an open cover, and there were some sets in it, and we gave them names. Okay. Here we made the open cover, and we made it with names, so they have these indices. And so when we write this, I mean, this would be the same thing as writing, in this case, that. Okay, but it's just easier because it got indices. What am I saying with that? Oh yeah, so if we had a finite subcover, that's really just a finite set of indices. Okay, so suppose that we did have a finite subcover. Suppose to the contrary, that U contained a finite subcover of our set. Okay. Well, then there would be some finite set of indices. Oops. Be some capital N and N. That would be, let's say, the largest index, so that our interval would be contained in the first, well, the 0 through the nth of these UNs.
Dr. Batter.
Yeah.
So, in this way that you've written it here, that's only including the ones that are sequential. But can we have like an indexing set that's like 1, 10, 15, 86, whatever? Because here, are we going from 0 to n? So we need 1, 0, 1, 2, 3, 4, blah, blah, n. Can't we include sort of, not randomly, but just natural numbers that are kind of wherever?
Yeah. Your finite subcover, the indices of your finite subcover are going to be, you know, arbitrary natural numbers. But there will still be a largest one of them, right? Because there's finitely many, there's always a largest, right? Call the largest index of any of them capital N. Okay? Well, now I'm going to say consider the even larger finite subcover, where I'll just give you all of the sets with indices up to capital N. Okay? That would be
Yeah, that makes sense.
this. It's all of the sets with indices up to capital N. Okay? That's possibly even more than you asked for. Okay? But this is a contradiction. Why is this a contradiction?
Because 1 over n plus 1 is, or, yeah, 2 to the minus n is not in it.
Mm-hmm. So one thing to notice is that these things are UNs are nested. They get bigger and bigger and bigger as n gets larger. So really the union of a bunch of them is just the last one. And that last one is that. Okay. But this is a contradiction. And it's a contradiction because we didn't cover everything. There are numbers that are smaller than 2 to the minus capital N, no matter what capital N is. Are there any questions on that example or that non-example?
So you said if this was a closed interval from 0 to 1, then it would
Yeah.
be 10.
Yeah.
So why would like the same argument not hold?
Okay, so if it's the closed interval from 0 to 1, then what I've given you, that's a great question. This open cover I've given you is not a cover. Why isn't it a cover?
Doesn't include 0.
Yeah. Now what if I throw in an open set that includes 0? Then what happens? So let's say we add in some open set. We're out of indices. So how about U star with zeros in U star? We add that to our cover. Now do we have a finite subcover?
because we can take the neighborhood around 0 and then take one of these UNs that overlaps it, and then we have a finite subcover with only 2 sets.
Yeah, exactly. Then we'd be back kind of where we were in the example, right? That U star that we added that contains 0, because it's open, it's got a neighborhood of 0 in there. Now that it's got a neighborhood of 0, it's got, we only need finite many of the U's to get there. In fact, in this case, our open cover would have a finite, quote unquote, 2 cover. Right? We could cover with 2 sets from the open cover. We would need the one containing 0, and then, U sub capital N for capital N large enough that it overlaps with the one that contains 0, and then we'd be good.
Do you mind explaining that again?
Mm-hmm. So if you look, if we take, we're in this counterfactual here, where our set was the closed interval from 0 to 1. And we took the same open cover together with some set U star that contains 0. And then we would say that there exists an epsilon so that the whole epsilon neighborhood of 0 is in that set U star. And then we'd say there is capital N so that what we'd want 2 to the minus capital N is less than epsilon. And then we'd say then U star union U sub capital N covers the closed interval from 0 to 1. Now, this was all an answer to a question of what would happen if instead of the half open interval we were looking at the closed interval. What we've just done does not prove that closed interval is a compact set, because to prove it's a compact set we'd have to consider an arbitrary open cover. Okay? But it does prove that this open cover has a finite subcover. Is that okay? So for today, the main goal is the definition of compactness and open covers and whatnot. This example and non-example. And then one more theorem. So that's going to be the last thing we do. It's also the next thing we do. Except before that, what does compactness mean for a discrete metric space? Any volunteers?
So in the with the discrete metric, every subset of the metric space is going to be open. So if you have an open cover that contains the set, we can. Oh man, I feel like I'm so close. The subset is going to be open itself, so that's going to be important. So, something like that. I feel like I'm close. I'm not quite there yet.
So compactness means you don't have any bad open covers. Now, discrete metric space means that you've got a lot of open sets around. So you put those together And compactness in a discrete metric space should be pretty rare, because since you've got so many open sets lying around, you're going to have a lot of bad open covers.
Can't you take, if you have an infinite subset, for example, you could have a cover being the collection of singletons of each of the points, so that's automatically not going to be compact.
Yeah.
But I'm not so sure about like a finite subset. I have to think more.
So this is the thing. In a discrete metric space, every singleton set is open, because every set is open. Okay. So if S is infinite, then there's an open cover of it. And it doesn't have a finite subcover. Why doesn't it have a finite subcover? Where there's infinitely many points in S. So you're not going to be able to choose finitely many singletons and have it cover all of S. Okay? So this shows no infinite sets are compact in a discrete metric space. Okay. What about the finite sets? Are they compact? Madeline writes yes. Yep, that's correct. Finite sets are compact. In fact, finite sets are compact no matter what metric space you're in. It doesn't need to be discrete. They're just finite sets are automatically compact. Why are they automatically compact?
Because you're gonna have, if you just take every point is gonna be in at least one of the open sets, and then you just choose open sets, one for each of them, and that's finitely many.
Yeah, you get your finite subcover just by picking out one open set for every point. And you've only got finitely many points, so you're guaranteed to have that be a finite subcover. Okay. Well, now you combine these two things in a discrete metric space. Compactness is the same as finiteness. Now, you already know on the real line with the normal metric, we're going to have more compact sets. That's going to be Monday. Okay. We've got 9 minutes. So we got a theorem. It's an if and only if. So I think we got time to do 1/2 of it, okay? And then the other half will be in the lecture notes. 1 second. I have to attend to things. There you go. Okay, let ZD be a metric space.
I want to send chips, Daddy. I want chips, Daddy.
Uh, Z is kind of a weird variable for our metric space. It's because we want a submetric space, X. And then K is going to be the set we're interested in. It's compact in the subspace if and only if it is compact in the big space. Okay. This is a really nice result. This says that compactness is intrinsic. Okay. What that means is that compactness doesn't care about the ambient space that you're doing this in. Okay. Now, if you think back to our definitions of open and closed, whether a set is open or closed can change when we change the enveloping space that we're interested in. Okay. But compactness can't. Okay. Now, don't take this too far, because we just talked about the discrete metric. If you go changing the metric, you will change which sets are compact. Okay. But as long as you keep the metric the same, and you're just changing the ambient space that you're looking in, then the compact sets don't change. Okay. Well, I mean, I guess. If you make the set bigger, you're going to get more compact sets. But anyway, you're not going to lose any compact sets. Okay. We okay on what the theorem's saying? So, in particular, if we're all in the, we'll use the standard metric on the real line. If you're compact in the interval from 0 to 1, then you're also compact on the real line. Okay, that's a nice result to have around. So I said we've got time for one direction. Let's see if I'm right. Suppose K is compact in the smaller set, the smaller space. Okay. Now we want to show it's compact in the bigger space, so we take an open cover there. Now, we took an open cover in the big space. Now we're going to define the script W to be the restrictions of all those open sets to the smaller space X. Okay? So we took all the open sets and we intersected them with X. Okay. Now, when you see openness and intersections, you should probably think back to our lecture on relatively open, or relative topology. It was like our fourth or fifth lecture. Third or fourth, maybe. What we proved there is that each of these intersections is actually open in X. By previous results. W is an open cover of K in the smaller metric space. Okay. Again, just remember, let's see. We defined relatively open with respect to X as being this condition, as being we defined relatively open with respect to X as being open in the metric space X, the metric space restricted to X. And then we proved that you're relatively open in X if and only if you're an open set intersect X. So these are all relatively open in X, which means they are open in that metric space. They already covered K, so they're already going to cover K. And, you know, K's in X, so we're not going to lose any points of X when we do this intersection. Okay. So we're an open cover there. Now, we assumed we're compact there. Since K is compact there, there is a finite subset V of U. Now,
Isn't V a subset of W?
Yeah, that's exactly what I was about to say. Yes,
Okay.
There's a finite subset of W. That's what compactness means, right? There's a finite subset of W. But everything in W is just something in U intersect X. So I'm going to write this as I want to think about the subset of U that I'm taking, and then I'll intersect it with X. So let me write this. That's what I want to say. So Daniel was saying I should take my finite subcover from W. But I did. I just wanted to say look at the corresponding sets in U, and then I restrict them. Okay. And the conclusion is that V is still a finite subcover of K in the big space. I The other direction, it's in the lecture notes, or it's a great exercise to think about it before I post the lecture notes. Otherwise, that's everything for today. Hopefully, shortly I will be posting the lecture notes, and I will also be posting a homework due on Wednesday of next week. So have a nice weekend. I will stick around for a little while if there are questions. Otherwise, see you Monday.